Welcome to this 16th lecture in Physics 10 in 30 lectures. With this lecture, we start Unit 3, covering the laws of classical physics. This week, we are covering thermodynamics, or thermal physics. And in this lecture, we will cover the background materials through the ideal gas law. In the second lecture this week, we will look at the laws of thermodynamics and how these laws operate in heat engines. So we start with an overview of Chapter 8, going over the topics you will see in this lecture. We'll do the part 2 of the overview later, alongside the heat engine material. Then we introduce the concept of heat, the transfer of thermal energy, usually from a hotter object to a colder object. With the help of PHYS simulations, we look at a microscopic view of matter as it undergoes phase changes and as it remains in gaseous form at high enough temperatures. We connect the mechanics of macroscopic pressure to microscopic collisions and the three dynamical quantities, pressure, volume, and temperature, that are being related together in the ideal gas law. And to wrap up this lecture, you will see that the boiling process cools a liquid, and we will go over some of the calculation questions from this week's exercises. Oh, and as a reminder, as you watch these lecture videos, many of them are old Physics 10 recordings, and some of them are borrowed from Physics 4B. Please remember that there has been a shift of chapter and section numbers. When you see references to Chapter 9 that appears to deal with the thermal physics, that is our Chapter 8 on the LibreText platform. And the references to the fluids chapter, which will appear as Chapter 8 on the CNX platform, it is our Chapter 7 on LibreText. Thank you, and we will start with the overview. Hi, this is the overview video for Chapter 8, Thermal Physics, Part 1. This is a long chapter, so we will break it into two parts. In this first part, we're going to cover the first half through section 8.7, phase change and latent heat, and the second half of the chapter covering laws of thermodynamics and the heat engines. We'll cover them in a second overview. Part 2. So, part 1. We're going to start from the beginning. So, a lot of this material might be familiar to a lot of people from your previous science classes. But for this introductory class, we're not allowed to assume that you have taken other science classes before. So, we'll cover everything from the beginning. If you haven't seen them before, then I do recommend skimming through the textbook. I think that'll help refresh what you already know. So let's just start out with temperature. So temperature is, I guess we define historically and maybe intuitively as how hot or how cold something feels. So, so if that's your intuition for temperature, that's great. That's almost everyone's intuition. Now, as far as the scientific definitions go, we get it most precisely in physics through our microscopic model. That's what this definition is referring to, proportional to average kinetic energy. Now, the definition of temperature you have seen before this class might relate more to how it's measured by a thermometer. So, people invented a thermometer that can kind of measure how hot or how cold something feels in a more objective way, and people have been using it long before we really understood what temperature truly represents, proportional to average kinetic energy, which we'll talk about more when we get to ideal gas law. So there are multiple temperature scales that's more related to how temperature is measured by thermometer. And we will mention three common ones. There's a fourth one that might be worth mentioning, but not too many people use it, so let me just skip it. So in US, you are probably familiar with the Fahrenheit scale. That's the scale set by the water freezing at 32 degrees Fahrenheit. and water boiling at 1 atmosphere under normal conditions at 212 degrees Fahrenheit. That defines the Fahrenheit scale, and the room temperature in Fahrenheit is something like 70 degrees. That's what you're probably familiar with for those of you in US and maybe Great Britain. The rest of the world, maybe including Canada, uses Celsius, where water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. I myself prefer Fahrenheit, but if you are used to Celsius, where room temperatures, I guess, more like 20 degrees C, then the word degree here indicates a kind of an arbitrariness to the scale. It's defined for common convention. So from my perspective, both the Celsius and Fahrenheit are arbitrary. That's why we say the word degrees Fahrenheit and degrees Celsius. The non-arbitrary scale that we will cover is the Kelvin scale. It's based on the Celsius scale, so the temperature differences in Celsius and Kelvin are the same. Difference of 1 Kelvin is same as differences in 1 degrees Celsius. But Kelvin is, in one sense, non-arbitrary. It's an absolute scale. 0 Kelvin means something very specific that 0 degrees Celsius frankly doesn't, property of water, that's so arbitrary. So at 0 Kelvin, the absolute zero temperature, what you can say is that the average kinetic energy of a particle goes to 0 at 0 Kelvin. So the Kelvin scale is the third, and that's really the scientific scale. When we talk about ideal gas law and other really scientific things, we'll be using Kelvin scale, and every now and then you can use the Celsius scale without losing anything, especially when you're talking about temperature difference. But when in doubt, in science classes, use the Kelvin scale. That'll almost never be wrong. And this is the leaf talking about absolute zero. It's 0 Kelvin. Again, that's how Kelvin scale is defined, and that's why it's the sole non-arbitrary temperature scale. And if you re-express in terms of Celsius so that people can get a sense of how cold that is minus 273.15. There are probably more numbers here, degrees Celsius. Yeah, minus 273. That's pretty cold. Liquid helium boils at around minus 269 degrees Celsius, or like 4 Kelvin. And at absolute zero, as I said, molecular motion ceases. The kinetic energy is zero. So that's temperature covered in section 8.2. Now, this mind map goes a bit out of order. I think the next section, section 8.3, is the ideal gas law. So the way we cover ideal gas law, we are kind of combining really, I think, centuries of work by chemists. And we are just combining all those different gas laws, at least 3 different gas laws that you might have seen in a chemistry class, and simply combining them into this one expression that says pressure times volume is equal to the number of gas molecules, ideal gas molecules, times this K, what's called the Boltzmann constant, times the temperature. And here it's important that this temperature is in Kelvin scale. If you accidentally use the Celsius scale, then this ideal gas law won't work. So at 0 Kelvin, 0 absolute temperature scale, pressure and volume of ideal gas is kind of forced, guaranteed to be 0. Because if the right-hand side is 0, then I guess either pressure or volume should be 0, but nothing actually reaches 0 Kelvin, so we don't have to deal with that. So the 3 gas laws that you might have seen in chemistry, they come from basically setting one of these 3 dynamical quantities, pressure, volume, or temperature, to be constant. So for example, when temperature is constant, you can say the change of pressure of an ideal gas is inversely proportional to the volume. Or if you keep the volume constant, then you can say the change of pressure is proportional to the temperature change, again measured in Kelvin scale. And if you keep the pressure constant, then you can say the change of volume is proportional to the change of temperature, again in Kelvin scale. And this one equation is the ideal gas law that captures all those three experimental phenomenological laws that chemists found. And we'll mention what we call kinetic theory of gas. And I don't think I do the derivation in this class because it gets a bit more mathematical. But in physics 4b, we actually derive ideal gas law from first principles using the mechanical principles that we teach in physics 4a. It's a lot of fun, but for this class, I do have a simulation that'll kind of demonstrate the underlying ideas and sort of the connection between, let's say, higher temperature and higher pressure. But we will fall short of actually doing the algebraic derivation of this law. Yeah, and describes the pressure, volume, and temperature relationship. There are some homework questions. Take a look, and I will also demonstrate some of those in separate lectures. Now the next textbook sections 8.4 and 8.5, heat and heat transfer methods. They are finally covered in this note. So heat and energy transfer, they are defined as, so heat is the one word where your everyday definition is not quite the same as the definition, the scientific definition that we'll use in this class. So the definition of heat is spontaneous transfer of energy due to temperature difference. It feels a little bit wordy. So in everyday language, I think you might say the word heat energy, or you might say this object has a lot of heat when you are referring to something that's really hot. So what we refer to as a heat in everyday usage, it's probably more precisely described as a thermal energy, which can be tied to the microscopic kinetic energy that the temperature actually measures. So that's the everyday meaning of the word heat. I recognize that, and I might even use it in that sense myself from time to time. But when it matters, the technical definition of heat is the transfer of that thermal energy due to temperature difference. So later on in part 2, when we cover laws of thermodynamics, we'll talk about spontaneous heat transfer. Spontaneous heat transfer occurs only from higher temperature to lower temperature. That sort of goes to the definition of heat. Now the methods. I think this is the one topic that I debated with myself if I should record a separate lecture or not. So the heat transfer methods, there are these three. They are explained in the textbook. And I think just mentioning and briefly describing them in this overview will be enough. I won't have to record a separate lecture for that. So there's conduction. That's kind of the heat transfer that commonly happens in a, let's say, solid material. If you have a long metal spoon or chopstick and one end of it is in a hot material, like maybe you accidentally put it on stove or you put it in a hot soup, and the other end actually gets warm or hot over time. That's the transfer of heat through conduction. No physical material is moving, but the energy is transferring through direct contact. The kind of the vibrating of the molecules kind of moves across that material. And I say it happens most commonly in solid, but you can also describe conduction in liquid and other states of matter. It's just that in states of matter that can move around, fluids, often convection will become more important. Because as fluid elements get hot through direct contact, through conduction, their density will change. Like they expand a little bit, so they get lighter, so they move away from the heat source, so they convect. There are some conditions that are necessary for convection to be occurring. And I guess the main thing is you have to be heating the volume of the material, that's a fluid, from the right location. So if your heating element is, let's say, at the top, at a higher point, then convection will be limited, because as things get hotter, they expand, they get less dense, so they will tend to float. But if they're already at the top, then there's no place for them to go. Now, a lot of everyday devices will kind of naturally cause convection because that's what people figured works well. If you're boiling water, you heat it from the bottom in a stove or any other device other than maybe microwave. And houses are designed so that sources of heat are kind of lower down, not high up. But every now and then you come across a situation where the placement of either heat source or the cooling source might limit convection. And we can also talk about the layers of atmosphere. The layer of atmosphere we live in, a lot of heating occurs when sunlight hits the ground. So this layer of atmosphere is heated from the bottom of the layer, so there's convection. But when you go higher up, like around where the ozone layer is, where sunlight is absorbed and heating occurs, that's sort of at the top of the layer. I think that's a stratosphere. And in that layer, convection doesn't occur as much, so the atmosphere is much calmer. A lot of commercial jet airliners fly in that layer to avoid the turbulent convection in the troposphere, the sphere that we live in. And finally, radiation, that's the fun one. It relates to something we'll talk about more later, electromagnetic waves. This is the transfer of heat without using any material contact. So there's something called the black body radiation that you will see more when we do, I guess, quantum mechanics. And that's a radiation that occurs whenever an object is at a temperature higher than 0 Kelvin. So at higher than 0 Kelvin, there's a microscopic movement of the atoms and molecules, and as they vibrate, they radiate electromagnetic waves. And electromagnetic waves carry energy. That energy can be emitted, can be absorbed. That's what's called radiation. So when you look at a device like a thermos, that's designed to keep hot things hot, cold things cold. There are design elements that's meant to reduce convection. It's double walled. Inside the double wall, there's no air. It's a vacuum. And also limit conduction. The wall is connected at only a very narrow spot to limit the amount of conduction. And the feature that's in a typical thermos that's designed to reduce radiation is the color appearance. A lot of thermos are shiny metallic object, have that kind of surface. And that's not just for aesthetic reasons. That shiny metallic appearance limits the amount of radiation. I mentioned the black body radiation, so that's in reference to what's called the black body. That's the ideal emitter and absorber of radiation. So objects that are black, like black in color, they when they're at a particular temperature, they will emit the most amount of this radiation that objects can emit at that temperature. Yeah, so 3 mechanisms of heat transfer: conduction, convection, radiation. And finally, the units of heat, the transfer, or the thermal energy. Joule is the one that I prefer the most, one that I'm most familiar with. That's unit of energy. And because, temperature measures the average kinetic energy per particle, and heat is the transfer of that average kinetic energy per particle. So it's energy, and we already have a unit for energy. That's a joule. And I like to say, if we knew all this way back when, we would have sensibly defined the temperature as something like joules per particle, because that is the natural unit for temperature. All the other units we have, like Kelvin, in some sense it's arbitrary. That's really why in the ideal gas law we have Boltzmann constant. Boltzmann constant converts from Kelvin to joules per particle. So that's the kind of the SI unit. And calorie, it's defined almost like degrees Celsius. It's defined based on property of water. I think 1 calorie of energy is how much energy is needed to heat up 1 gram of water by 1 degrees Celsius, maybe. In this class, you will see both the calorie or kilocalorie and joule. I think there's one of the homework questions with a chart where the x-axis is in kilocalorie. But we won't be doing a lot of calculation using either unit. Okay, so that's sections 8.4 and 8.5, heat and heat transfer methods. And the last set of sections that we'll cover in this overview is sections 8.6 and 8.7, temperature change and heat capacity, and phase change and latent heat. And in this overview, I think that's under thermal properties of matter. For some reason, Notebook LM put it out of order here. So under the thermal properties of matter, heat capacity is what we talk about when there's a change of temperature and we want to relate that to the amount of heat transfer. So we define a quantity called specific heat. It's a material property, almost like a density. It's the I think I can talk about it a little bit better with this formula. In this formula, Q is equal to mc d. I think that's meant to be delta T. So Q, that's the heat transfer, amount of heat transfer. So this is like change of energy. And on the right hand side are the parameters that can affect that transfer of heat. The number one property here is what they're labeling as dT, delta T, change of temperature. So this formula is trying to relate the transfer of heat energy to the change of temperature. And some of the quantities you can kind of guess. You can guess that given the same change of temperature, if you have more material, then it probably takes more energy. And that's what this M represents, amount of the mass. So total amount of heat transferred will be proportional to amount of mass. You have double the mass, you will need double the heat energy, thermal energy, to change the temperature by the same amount. And that's where this material property C, specific heat, comes in. So there are some materials that have high specific heat. Water is the typical example. So with the materials with a high value of C, given the same amount of material and same amount of temperature change, you will need more heat energy, more thermal energy to change the temperature by the same amount. That's what having high specific heat means. And conversely, with the low specific heat, either you can say it takes less amount of thermal energy to change the temperature by the same amount, or you can flip it around to say, given the same amount of heat energy, lower specific heat means the change of temperature is greater. And the most common example you might see is one of the microclimate. So the Bay Area has such a temperate weather because we are right next to the ocean, the big body of water that moderates the temperature swings between night and day and between different times of the year. But if you go inland, far away from large bodies of water, the ground has lower specific heat, so given the same thermal energy from the sun through radiation, the change of temperature is greater. And the last section we are covering with the phase change, that's the fun one. Latent heat is the idea that there's a thermal energy associated with the change of phase, going from solid to liquid, liquid to gas. And one of the things that's quite surprising the first time you see it is that the latent heat of vaporization, how much energy it takes to boil water, is pretty large. So I think there's one homework question that shows that this diagram of amount of heat transferring into what starts out as a really cold ice, and it's going to eventually turn into steam, and the majority of that energy input is spent at 100 degrees C, boiling the water away. So with the latent heat, these are the kind of the technical terms for different phase changes. Fusion, latent heat of fusion is amount of energy needs to turn solid into liquid, or you can flip it around to say that as liquid freezes into solid, it gives up that much latent heat, releases into the environment. Latent heat of vaporization is when liquid, like water, turns into gas, like water vapor or steam. And sublimation is the less common one. I guess the most common example you might see of sublimation is the dry ice, which is the frozen carbon dioxide, CO2. And it goes from frozen, solid, dry ice to gas, CO2, like without intermediate liquid step, at least at 1 atmosphere. If you put it under a great deal of pressure, you could turn it into carbon dioxide liquid, but that takes a lot of equipment and effort. Yeah, so that's latent heat. There is a lecture video where you will see me say boiling is a cooling process. Take a look. It addresses some of the really counterintuitive thing about the phase change and the heat transfer associated with that phase change. So that covers the last of the topics that we'll cover in this overview, part one. Temperature, ideal gas law, going in order, heat and energy transfer, and thermal properties of matter. These two remaining nodes will cover it in part two, as we are really talking about heat engines. That's what I'm excited about, but you will see that in part two in a separate video. Thank you. We will start out with the first lecture video.
So I guess I can just start section by section. So 9.1 temperature, define temperature. I feel like most people here do know about temperature. Maybe you might not be familiar with different scales. I think there you probably should read about it. But I think what I could talk about that actually relates more to section 9.3, defining heat as a transfer of energy, is talking about just the different forms of energy. So this is one of simulations on FET. So I'm in the heat and thermal section of the FET, phet.colorado.edu website. It's a great website with a lot of fun simulations that are totally free, and they are high quality, and it's very, I don't know if they're well funded, but I think they had a grant from National Science Foundation to make initial set of simulations. It's really a great resource for learning physics, chemistry, and I think once you're on this website, they also have math and other materials too. So I just wanted to use this energy forms and changes simulation to just talk about different forms of energy. Because up until Unit 2, we quite deliberately limited ourselves to mechanical energy, that is kinetic energy, and a few forms of potential energy. You've seen gravitational potential energy and spring potential energy. And as we talked about when I was introducing energy a few weeks ago, the defining characteristic of energy is that it's a conserved quantity. And when mechanical energy changes form into something else that's not mechanical energy, we define new forms of energy so that the total energy is always conserved. So I guess I should have looked at the simulation before, but let me start out with the intro. So I guess I don't really necessarily know what I'm doing here. I don't know if I like this intro. I could. I guess we can use this to talk about temperature. So what we can do is we can put an iron and brick block here. And what I think I can kind of do to illustrate is what happens to these two blocks as we heat them. So just to illustrate the simulation, I have some control here. I can apply some, it doesn't stick. Oh, link heaters. Okay. So I can make sure I apply the same amount of heat. Okay. So I have iron block here, brick block here, and as I heat them together, so you have some intuition about heating things, and you know their temperatures will change. Now, I hope you have this experience. When you heat things, as you heat them, things don't heat up necessarily at the same rate. And that's what you are seeing here. That as I heat up iron and brick, and these two heaters are linked, heating them, I'm transferring some amount of energy in some form at the same rate, but the brick block goes up in temperature faster than the iron block is doing. So something's different about that. And okay, I guess when I don't apply heat anymore, I don't know what's gonna happen. And Is brick block going down faster? And one way to cool down these things is to put them in water. And when you put them in water, then what you see is that the temperature of this block changes a lot. It cools down quite a bit, and the water warms up a bit, but doesn't warm up quite as much. Interesting. And if I were to do the same thing with the brick, putting it in olive oil, then what you see is that oil maybe goes up in temperature a little bit more. Was it because of difference between iron and brick? And this is where you can spend a lot of time doing experimenting. And I guess what I want to leave you here with is there is a connection between temperature and what we call heat energy or thermal energy. And for most of the material, the connection is not trivial. It's not. It's like a relationship that really depends on the material you're talking about, how much there is, and all that stuff. So you can so one thing that you can rely on is the temperature that you see and the amount of energy that we are going to call thermal energy or internal energy. That relationship is linear. So that happens to be kind of easy to understand. But beyond that it's linear. How the temperature exactly corresponds to the thermal energy, it's going to depend on the material. But I want you to start out with the intuition that there is a connection, even though the exact formula is maybe a little bit complicated. That's why we do have an experimentally determined relationship called specific heat capacity that you are going to see addressed in the textbook. So read about that. And and I think systems will tell us a little bit about how you can convert different forms of energy into different forms. So here we have one form of energy. So we have water that's in the pipe, and when we turn the spigot on, the water is falling down. So what you are seeing happening is the water is at some height here. So that water is turning, it has potential energy that's turning into kinetic energy. So this is what you've seen in Unit 2. It's just happening with water, nothing fancy. Now, one thing that's a little bit kind of waste here is, okay, so that potential energy turns into kinetic energy, and then nothing else happens because I have a wrong device here. I have a solar panel which doesn't do anything with this water. So if I have a water mill instead, then what happens is that, can I get rid of, I guess I need to have something here. Well, then what happens here is this mechanical energy of the water, or the momentum of the water as it's colliding with the wheel, it's imparting the momentum, it's also transferring kinetic energy, and the kinetic energy is turning this wheel. And there's some device here, something similar to what they have in hydroelectric dam, that's turning that kinetic energy, mechanical energy, into electrical energy. And that electrical energy can be used to do various things. Right now it's turning a fan. It could be used to turn on a light bulb, or it could be used to turn on a more efficient light bulb. It doesn't look more efficient. Well, supposed to be more efficient. Or it could be turned into heat. That's what this heating coil is. And when there's water on top, it's turning the, increasing the temperature of the water. And I think if I put it energy symbol, then what this illustrates is kind of transfer of this energy into different forms. So here, this gray block of energy is mechanical energy. This blue block is electrical energy, turning into thermal energy, which is leaving the water as water evaporates. And I guess here it's not that much energy, so it's at some equilibrium where water is steaming but not boiling. And you can play with this to see how different. Oh, now I need a solar panel. Different. It's I guess it's not this description. It's a good background material for those of you who haven't seen this in your middle school, high school science class. I think all this is intuitive, and this is really where we do get our conservation of energy from. Energy is a sort of poorly defined concept where the only one thing that we hold true is that it's a conserved quantity. And when we talk about thermal physics and thermodynamics, what we are going to look at is the conversion, transfer of energy from form that's not thermal form into, or I guess actually the main use of thermodynamics is how to convert energy that's in this thermal form into mechanical energy. And I think there's actually an example of that here. Let me see. Yeah, this is an example of that here. So here we have a form of energy that's starting out as a thermal energy. And you see that as this water pot boils, that thermal energy is turning into mechanical energy. And now you need some other device to harness this mechanical energy, otherwise it'll just turn back into thermal energy, which can be used to do useful work. And one way you can do that is something like this, a wheel, or in a more practical sense, a steam turbine at a power plant that burns fossil fuel. So, so this is kind of showing how you can take energy that starts out as thermal energy into mechanical energy, which is really the form of energy that is most useful. And there's a device here which will turn it into electrical energy. And we're going to get to that in chapter 11. That's one of the reasons electricity and magnetism is such an important thing. And this electrical energy is really the most versatile form of energy. It's the most useful form of energy in our modern life, because we have all these different devices that are able to do different things with this electrical energy. It can be used to generate light, and it can be used to do other right now light, and it can be used to also do other mechanical things. There's something called the electric motor, which we'll get to in chapter 11, that turns this electric energy back into mechanical energy. So I hope you have this intuition, or if you didn't, then this simulation, you can play with it yourself, and that it's helpful. All right. Do I want to talk about friction? Well, I guess I can talk about friction briefly. We did talk about friction starting with the unit 1. Like, friction is what we blamed when we apply a force on this object, and we kind of stop applying force. It stops, and friction is what we are blaming on, why the motion doesn't continue after you stop applying force. And friction is also what we blamed on for non-conservation of mechanical energy, as in whenever it seemed that mechanical energy wasn't conserved because something that's moving on a non-frictionless surface comes to a stop, so the kinetic energy that had before disappears. Where do they go? We said it goes into heat and sound, and how. And this is kind of the microscopic view that illustrates how that happens. So the way you should look at it is every surface, when you go down into small enough scale, is rough. So as two things slide against each other, there's work being done on these two molecules from those rough surfaces and edges. And that work being done, it actually goes into mechanical energy. microscopic mechanical energy of these molecules. They are vibrating more because they are receiving more mechanical energy. And that vibration at our macroscopic scale is felt as increase in temperature. That's what this is showing. So, if you want to turn mechanical energy into heat, we know many ways to do that. One of that is just to use friction. So that's what this simulation is showing. So I just want to use a simulation to show you how that looks like. So I think one of the simulations that will let me do that is states of matter. Let me do basics just so that I don't get lost with all the controls and whatnot. And really, a gas is the simplest state. And I guess I can kind of demonstrate here why it's the simplest state. So this is the microscopic representation of a solid. So I hope everyone knows that everything is made up of atoms, right? Yes, hydrogen, helium, lithium. As far as I remember, those are all atoms, examples of atoms. Hydrogen is made up of proton and electron, and helium is made up of 2 protons, 2 neutrons, and 2 electrons. Everyone knows that. But I guess what's important for our purposes here is that when you look at a solid object like this, it's made up of indivisible, very small particles. And that's what this illustration of solid is showing. It's showing you those individual microscopic particles, atoms, I guess neon atoms, and it's somehow bound together with each other. That's how a solid maintains its shape, and that's something that makes the solids kind of complicated. Because if I want you to just look at motion of this one neon atom, that's going to depend on all its neighbors. So treating solid from this microscopic fundamental view is pretty complicated, which is one of the reasons I was saying that the relationship between temperature and the thermal energy is complicated. It's not something you can easily derive. You hopefully are also aware of liquids as a phase of matter. And the defining feature of liquid is that it takes the shape of its container. I think we covered the liquids in chapter 8. Let me just double check to be sure. Unless the fluids. Did we talk about states of matter in fluids? We might not have, because states of matter will, so we didn't talk about states of matter because that needed a thermal physics, but using liquids in the chapter 8 with the fluids. And with the, liquid type of fluid, the defining features, takes the shape of the container. And liquids are actually just as complicated as solids are. And you can see why. If I wanted to follow this one atom of neon, then it's constantly interacting with its neighbor. It's always colliding with its neighbor. So tracking this one neon atom in a liquid it's a complicated business. So we don't do it. I guess I've been talking about neon, but I could have talked about water. Why didn't I do that? So this is an illustration of ice or solid water. It's supposed to be hexagonal, but I guess in this 2D representation, it's not really. So this is solid. You can see that the relative relationship between neighboring water molecules stay more or less constant. When it's a liquid, then one water molecule can move past another water molecule, but it's still constantly interacting with another water molecules. So this is why gas is simpler. When something like water or neon is in a gas state, then these atoms or molecules are very far from other atoms and molecules. So you can see these occasional collisions So can I slow this down? I can't. Okay, I can pause. Let's say you are tracking this neon atom, and just watch it for about a second or so. Then you can see that it took maybe fraction of a second. Let's look at this neon atom. It seems far enough from some other things. So it takes, okay, it took about a second before that neon atom collided with another neon atom and changed the direction. So with the gas phase of matter, these gas molecules or atoms, they interact very rarely, well, or relatively rarely compared to liquid and solid with other molecules. That's what makes gases simpler. So that's actually the starting place for what we call ideal gas. With the ideal gas, we ignore all these interactions between atoms and molecules in the gas phase. So here, with the real gas, you see them colliding with each other occasionally and all that. So with the ideal gases, the approximation we make is approximation that these gas molecules don't interact with each other. You can kind of imagine it's going through each other. I mean, here it's not doing that, so it's hard to, but with ideal gas, we still look at the fact that they're interacting with the walls, and that'll give rise to what we call pressure, or what we call the pressure in chapter 8. So one description of thermal energy you can give is microscopic kinetic energy. So when you have these microscopic things that are moving around faster, so they have more kinetic energy, then from the macroscopic description, we look at it and say it has more thermal energy. And we can measure that thermal energy in a more direct way using a thermometer. Let me do the phase shift, actual phase shift. So when you change from solid, as you heat it up, this is what happens. You see those vibrations happen more. So with this increased vibration, what happens is that, so those molecules are bound tightly together because they have very little kinetic energy, and there's some interaction between the atoms that's so that leads to kind of a lower potential energy. It's like, imagine being an object being closer to Earth. When it's closer to Earth, it has lower potential energy. So in a solid state, it starts out with a very low potential energy. As you put in more energy, you are putting in the kinetic energy, which helps it overcome that potential energy barrier. So it's kind of, the atoms are kind of separating from each other. So they have less potential energy, more kinetic energy. This is liquid state. And as you heat it up more, it has more and more kinetic energy. At some point, it has enough kinetic energy that atoms can be unbound from each other. So the attraction between them is small compared to, or the potential energy associated with the attraction between them is much smaller compared to the kinetic energy. That's when you get the gas stage. All right, let me, so I think to talk about the change in the thermal energy and pressure, I think I need to go to the other tool. This one doesn't, oh wait, this one does. Phase diagram. Do I want to do water? Yeah, let's do water. I guess let's try heating it. And when you hit it, this is, oops, I want you to look at the phase diagram. And how do I explain this? Well, I mean, it's plotting pressure and temperature. I think you have some intuitive feel for that. Right now, this block of ice is in a solid phase. It's in all kind of on that boundary. So as you heat it up, you increase its pressure, temperature. Then you see its temperature increasing. And it says pressure increasing. And what it's referring to is something called the vapor pressure. You can ignore that for now. So at this point is where it kind of, it's at high enough temperature where it it forms into liquid. So right now it's at the boundary between liquid and gas. And you might ask, what do you mean boundary? Well, let me heat it up a little bit, then you can see it a little bit more easily. And what you see is some of these water molecules kind of separate from the body. This is what we call evaporation. This is when the phase change happens on the surface of liquid. The water molecules are returning to water, some are leaving the water and becoming gas, water vapor, and this is at some kind of equilibrium that's associated with that temperature. That seems way too high. And so that's what this means. That's what why it's at the boundary between liquid and gas, because some portion of it is in liquid, liquid, and some portion of it is in the gas form, and what pressure at that gas form is at is illustrated on this phase diagram. And once you heat it up enough, and oh, I see why this is at such a higher temperature, and I had some gas left. It's because it was at higher pressure. Yeah, maybe, I don't know. As you keep increasing, and at some point it's at high enough temperature that it's just going to be at gas phase or some intermediate phase that's, I don't know, looks like a gas, but okay, that part you'll have to ask a chemist. I don't really use the phase diagram that much. I really want you to talk about the ideal gas law, which I guess I placed it into the background section of the chapter. And really the biggest reason for that was you could have seen it in your chemistry class. I guess high school chemistry class. I don't know how many people taking this class are or have taken Chem 30, although you could have. But ideal gas law, you might have seen it in many different contexts. It's a fascinating law, how they discovered it. It was originally discovered by chemists. And the way chemists discovered it, it's a really great detective work. And I think you see this more properly introduced in chemistry class as a combination of different gas laws. Because there's I don't know where it is, Boyle's law, if it's in the textbook, yeah, I guess I talk about that somewhere here. It comes from Boyle's law, Charles' law, and there's some French name that I'm forgetting. But so ideal gas law in chemistry gets introduced that way, as a combination of many different, not many, 3 gas laws. Now, the physics treatment that I want you to see, and I want to illustrate with a simulation, is the microscopic treatment, or what we sometimes call kinetic theory of gas. I don't know if I use that phrase in this textbook, kinetic theory of gas. It's basically looking at oh, yeah, it comes towards the end of the chapter. You will get to that. So I just want to use a simulation to show you how it relates to pressure, all that. So, so here's one thing you see. Do I have pressure meter? I don't have pressure meter. So this is what I want you to see. So let me first turn this argon into gas. And then we'll talk. All right, so it says it's at, well, freezing temperature, 273 Kelvin, but argon is a noble gas. There's much less attraction between them than water does, so it's already a gas phase. And this is what I want you to notice, and why I needed this, something that was measuring pressure. So right now, there's a pressure built up in this vessel. And according to the measurement that this pressure meter or barometer is making, it's at about 30, let's call it 30 atmosphere. 1 atmosphere is pressure equal to that exerted by gas in atmosphere. So it's at 30 times that, which I guess I'll just have to take its word for it. And you can increase pressure of this vessel in different ways. One way is to just apply more pressure, push it down, that will increase pressure. And a second way is you can add more heat. So let me go from 273 Kelvin and about 30 atmosphere to let me just double the temperature. Let's go to 500 Kelvin. So let me just heat this up to 500 Kelvin. Then I want you to look at what happens to pressure. And I hope to explain that in a couple of minutes when I'm at 500 Kelvin. So when I am at 500 Kelvin, this is what you see. So you see the argon atoms bouncing around more, so they are moving faster. And that's somehow leading to an increase in pressure. So you might ask, how is it doing that? And you can understand this in terms of momentum and impulse. Each time these molecules bounce off of the surface, it's imparting momentum. It's it's giving impulse to the wall. That impulse transfer is happening over some fixed amount of time. So when you get that impulse divided by time to give you rate of change of momentum, that's the definition of force. So there's a force on this top surface that you can base on the transfer of momentum, which represents force being applied. And when you take that amount of force, divide out the area, that's when you get pressure. Pressure is force over area. So what this has shown is that as these argon molecules are bouncing around, as it collide with the surface, it's imparting some momentum, which becomes kind of force on that plane. And can you see why that force, hence pressure, should be increasing? I hope you can. And the reason is that if these balls are moving faster, then it's imparting greater amount of momentum in the same amount of time. And actually, it also becomes a shorter amount of time because the rate of frequency at which it collides also increases. So in a class like a Physics 4a, I actually do this derivation. It's a lot of fun. For Physics 10, I just want you to have that intuition that when you heat something up, not something, when you heat up a gas, the pressure increases because of this consideration of collisions, which will involve momentum change, which will be tied to force applied, which can be tied to pressure exerted over a surface. Okay, so you have that. Let me cool this down so that next time I do something, it doesn't break the simulation. It has done that before. I think the biggest problem is that it doesn't simulate enough number of gas molecules, so it's gonna run into numerical issues. It's by the way one of the reasons why the pressure fluctuates so much. When you actually measure real pressure in real gas, it's usually like stable in a part in 10,000 or something. The reason this is fluctuating so much is because what we are simulating here so much smaller by fraction by to a gas amount of gas in an actual room that so much smaller that there's no real SI prefix for it. So I think it's like 10 to minus 20. So anyways, so here's one other way you can increase pressure, and that's to press it in. So as I press it in, you will see that pressure goes up, and part of that is, well, I'm applying force. So, so yeah, of course pressure goes up. But here's one other weird thing. You can see that as I pressed it down, the temperature went up. How come? Why? What's going on? And as I pull this back up, you see temperature going down and the pressure going back down. what's up? I just want to leave with that this is the kind of introduction to thermodynamics. It's how work being done by force being applied over a distance turns into thermal energy. and how when the gas does work on the lid, that energy, the work being done on the lid, comes out of the thermal energy. That's the thermodynamics part. That's the part you're going to get to in the second part of chapter 9. So let me continue on with the remainder of the introduction to background material for thermodynamics.
See, question 4. I think you can do it. Yeah. I mean, so what the hint is getting at is when you look up the formula in the textbook, then you will see the ideal gas law, which says PB equals NkT. And the thing to be mindful, careful of is knowing which ones are dynamical quantities. The dynamical quantities, as in properties of gas, there would be P, V, and T. And the thing to be careful about is we've used these letters to mean different things before. Like we've used the P to mean momentum before. We've used the V to mean velocity. And we've used the T to mean time. And it doesn't mean any of those things. The capital P here stands for pressure. The what's ideally capital V here stands for volume. And what's capital T here should stand for temperature. And I think the main reason I was asking this question was because, sometimes people fixate on formulas and forget that what's more important is not the mathematical expression itself, but what it represents. I like to say each formula tells a story, and it's more important that you know that story than knowing PV equals NkT. I, I don't care if you have them memorized. I care that you know what kind of relationships ideal gas law represents. So let me just move on. I can answer it, but let me move on. Uh, oh yeah, I think this is I think it's worth answering. So let me answer it, and then I actually do talk about this in one of the videos. I'll highlight that. So So the question is asking the question: ideal gas law allows you to predict how properties of a gas change under certain circumstances, given an initial change, correctly match. Okay, so let me rewrite down ideal gas law so that I have something to refer to, and I'm gonna strip it down to bare bones. I'm not gonna write down the coefficients and constant because really the ideal gas law expresses is pressure times volume is proportional to temperature. It's a combination of all three gas laws that you might have seen in chemistry class or whatnot. And so let me go through each of the choices. It says pressure is halved and volume is tripled. Oh, so I'm looking at pressure and looking at volume. If this goes down by a factor of 2, that's what halved means. This goes up by a factor of 3. Then combined, the product changes by a factor of 3 halves, so increases. So temperature would increase. That would be C. Pressure is increased, keeping volume constant. So I'm looking at this expression here. Volume is constant, so I don't have to worry about that. It says pressure is increasing. Then temperature has to increase. There's no other choice. Okay. So temperature increases. And okay, this choice says volume is increased. And I want you to note here how, as you are looking at these three quantities, that you're not given enough information. You are told that volume is increased, but it didn't say anything about pressure. Is the pressure constant? Is the pressure also increasing? Or is pressure going down? Going down just the right amount to keep the temperature constant, or going down so much that temperature is actually decreasing? There's just so many possibilities there. So for this choice, the answer would be not enough information given.
And I find that that's sometimes the biggest mistake people make when they work with ideal gas law. They just see, oh, volume is increased, and there's one of the gas laws. I forget what it is, Charles law or Guy Gate. I forget all these names. Um, and sometimes people just remember one of those gas laws and forget that for one of those gas laws to hold, you have to hold some of these quantities constant. And ideal gas law deals with the most general case. So unless someone tells you that pressure is constant, you shouldn't assume that it's constant. Okay, so volume is decreased and keeping pressure constant. So here, okay, they said the pressure is constant, so we don't have to worry about it. So if the volume is decreasing, then temperature must be decreasing. So temperature decreases E. Pressure is decreased. This is the same deal. They didn't tell me about volume. Could it be increasing? Could it be decreasing? Could it be decreased, or could it be increasing so much that despite the decrease of pressure, the temperature is increasing? Anything could happen. So not enough information. Pressure is increased while volume is decreased in inverse proportion. Oh, I think what it means is when you multiply them together, that the product is not changing. So temperature remains the same. A. And I guess I'm never selecting B or D. Um, yeah, I think choices B or D are there so that people might, for these, might mistakenly choose them. Unless they tell you something about the temperature from the fact that volume increased, you cannot infer that pressure necessarily decreased. Now, if they told you that temperature is constant, then you would be able to infer that. But if they don't, you don't have enough information.
Hi, this is lecture video on phase change and heat transfer, or boiling is a cooling process. So you all know about the three phases: solid, liquid, and gas. Or if you are sophisticated in your understanding of phases of matter, you might even know about the phase diagram, which shows different states matter can exist in depending on ambient pressure and temperature. Generally, at a given pressure, the hotter the material, the more likely it is to be in liquid phase or gas phase. Or at a given temperature, you could force gas into liquid state by applying more pressure. And this is the phase diagram for water. This is a sort of a general phase diagram for some substance that shows the same idea. The hotter the material, the more likely it is to be in liquid or gas phase. And the higher the applied pressure, the more likely it is to be in liquid phase, and possibly in the solid phase if it's in the right temperature zone. When you want to change phase of matter, boil water for example, what you normally do is transfer heat. And many of you know about different heat transfer mechanisms: conduction, convection, and radiation. So that's what forms and informs our everyday intuition. Taking water, for example, when you cool it down, put it into freezer, for example, and it freezes. It turns into solid. When you heat it up, maybe put it on a stove top, and it boils, turns into gas. There are lots of everyday experiences that go into forming this intuition. Boiling, hot; freezing, cold. What would you say if I told you your intuition is misaligned? Specifically, boiling is a cooling process. A liquid is cooled when boiling occurs. It's not an easy thing to believe, so let me show you a video. For this video, a test tube of water was placed in a bell jar. and the air inside the bell jar was vacuumed out. The water begins to boil when the ambient pressure is lowered enough so that it is equal to or less than the saturated vapor pressure of water. Intuitively, the ambient pressure was pressing water molecules together. So when the pressure is lowered enough, water molecules separate from each other, turning from liquid to gas phase. Now watch carefully. As the water continues to boil, the temperature of the remaining water starts to decrease. And if I had a better pump, I could boil this water until it begins to freeze. In fact, you can find videos where people do that by searching for the phrase freezing by boiling, for example on YouTube. But is this cooling something special that happens only with the special equipment like fancy vacuum pumps? This is where I want you to read figure 1.15 carefully. Figure 1.15. This is a plot of temperature of a substance which starts out as ice at minus 20 degrees Celsius, and you start to apply heat. On the horizontal axis, we are plotting the amount of heat added per mass. We can imagine we have 1 kilogram ice to start out with. So this would be 1 kilojoule, 2 kilojoule, and so on. As you initially add heat, the temperature of the ice increases. And this flat part is where ice is melting into water. The temperature begins to rise again after all the ice has melted, and then flattening out where water is being vaporized, that is, boiling into steam. And when all the water has been turned into steam, the temperature of the steam rises again. I hope this graph doesn't seem unfamiliar. If you have not seen this graph before, I hope this at least makes intuitive sense. After all, this is how we define a melting point and a boiling point. When you have a mixture of ice and water, if they are all well mixed into a thermal equilibrium, you know it is at 0 degrees Celsius. When you have boiling water, mixture of water and steam, as long as it is boiling at 1 atmosphere of pressure, you know it is at 100 degrees Celsius. You don't have to know how long the pot of water has been boiling to know what its temperature is, as long as there is some water left. Now, here's what I want you to consider. If, as you go along the horizontal axis, you're adding heat, why isn't that added heat showing up as temperature of the ice water rising, or temperature of water and steam rising? Your textbook talks about latent heat of fusion for melting, and latent heat of vaporization for boiling. This is the amount of heat needed to break bonds between molecules, turning solid into liquid and liquid into gas. And here is another way to look at this. This breaking of bonds takes energy. You have to put in enough energy to free a molecule that's bound to a neighboring molecule. When this energy is taken from the surrounding is cooled by this process. This is why you see, as the ice melts, the temperature of the mixture stays constant, because the cooling effect of ice melting is exactly taking away the heat input from outside. And this is also why, as the water boils, the temperature of the mixture stays constant, because the cooling effect of water boiling is exactly taking away the heat input from outside. This latent heat of vaporization is quite substantial. As you see in this graph, it takes more energy to boil 1 kilogram of water already at 100 degrees Celsius then the amount of energy it takes to bring 1 kilogram of very cold ice to 100 degrees Celsius. You can look at the distance along the horizontal axis to see how much heat it takes to boil away all the water. Over the next few weeks, we are going to be referring to internal energy quite a bit. Please remember that the kind of internal energy we will be interested in comes in two primary forms, kinetic energy and potential energy. In both cases, we are talking of kinetic energy and potential energy of microscopic objects, molecules. All molecules either bounce around in gas and liquid forms or vibrate in solid form especially. The kinetic energy, the average kinetic energy of this movement is reflected in the temperature measurements. The potential energy of molecules, since most molecules attract each other through intermolecular forces, the farther away molecules are from each other, there is more potential energy. And this is reflected in the state of matter. The solid state has the most negative potential energy. It requires the greatest amount of energy to free the molecules from its neighbors. And the gas state has the least negative potential energy. To a good approximation, it's zero for many gases at room temperature. In fact, that's the ideal gas approximation. So this internal energy isn't really a new form of energy. It is still a form of mechanical energy, potential plus kinetic energy, when you take the molecular view of matter. To wrap up this video, please think about situations when you are near a substance, well, most likely water, that was turning into gas, evaporation, or turning into liquid from gas, condensation. In which of the two did you become cooler than you otherwise would have been? In which case did you become warmer? Okay, so here's a calculation question. It says, using the ideal gas law, PV equals NkT, and this is pressure times volume is equal to N, number of gas molecules, times K, Boltzmann constant, times T, temperature. In Kelvin, this is where the units are important. Well, units are always important, but this is where people can easily make a mistake of using temperature in Celsius or Fahrenheit. So it says, find the number of gas molecules in an ideal gas at this amount of pressure in a volume of this much volume. All right, at a temperature of, okay, it gives us temperature in Kelvin, so we don't have to do any conversions. All right, now, just as a kind of double check, let me look at what hint says. It'll probably has a, well, it says a review, and wonder if you review, it'll have this equation actually solved for n. Let me just double check. It might not. If it doesn't, then I will show you solving for n. If it doesn't, I'll point you there and kind of copy the equation and just use that. Yeah, I guess it doesn't solve for n. I think one of the examples to calculating the number of molecules in a cubic meter of gas. So so it actually solves for it here. So I hope this step makes sense. In the process of copying, let me kind of do the quick derivation. Let me bring up the annotation tool here. By the way, I changed my zoom setting so that now you see my zoom windows. This is kind of what was not visible before, but now it's visible. I don't know if that makes a big difference either way. So we have this equation here, PV equals NkT, and I'm going to write it on the side so that I can continue to use it once I switch the tab over. So pressure times volume is equal to number of gas times the Boltzmann constant times the temperature. And your goal is to solve for the number of gas. So I look at this equation and I see that in order to get n by itself, I need to get rid of k and t from the right-hand side. And the thing to do is to multiply both sides by an expression that will help me get rid of k and t. This is where I hope you remember from your algebra class that if you are doing the exact same thing to the both sides of an equation, then you are not changing anything. So what I want to do here, especially on the right-hand side, is multiply the right-hand side by 1 over kt so that I can cancel out k and t here. Now, if I did only this, then I'm changing the equation. I shouldn't do that. So I have to do the same thing to the left-hand side. Multiply left-hand side by 1 over kt. Then k and t cancel on the right-hand side. So I'm left with just n. Let me write that down here. N is equal to, and on the left-hand side, which I'll write on the right, I have P times V divided by K times T. So P times V divided by K times T. And that's what you see here. So I could have just copied it, but did the derivation. So, all right, let me switch my tab over. So all I need to do here is I just need to plug in the numbers into this formula here, which was worked out in that example. This formula here, which was worked out in the example. So let me bring up a calculator and do that. As I'm plugging the numbers, I'll be minding these units, and I'll be careful in entering very small numbers like this, because I have to enter it very carefully in scientific notation. So let me bring up the calculator here. All right, so pressure, it says the pressure we're given is 100 kilopascals. So I have to remember that, so I'm going to try to plug in all the numbers in the basic SI units. So when I'm given the numbers in kilopascals, I'm not going to plug them in kPa, because then it's not a basic SI unit, so not everything will work out right. So I will keep in mind that 1 kilopascal is 1,000 pascal. So when it tells me 100 kilopascal, in my calculator, I'm going to put in 100 times 1,000 for what it is. So, okay, that's my pressure times the volume. It's already given in the basic SI unit of meter cubed. So I'm going to leave that unit alone. So I can just plug in 0.8 for my volume. Okay, now I need to divide by Boltzmann constant. And this is where you have to be careful. You have to know how your calculator works. So let me demonstrate here with how I know the calculator works. So I'm going to use the E notation. It uses this EXP key. And the way it works is, first, I plug in the leading part of the scientific number, which is here, 1.381. 1.381. And when I type in the EXP key, it'll give me an option to put in additional number here. And that additional number in the E notation, the number that goes there is this power of 10. So it's gonna have to be minus 23. And the only way I can enter that here is actually type in 23 first, and then this key to put it into minus. So you see 1.381 E minus 23, and that's the number I'm dividing by. Okay, I have one more number I'm dividing by, that's the temperature. So I do another division, and then 278 equals, I get that humongous number. I think I'm not going to bother writing it down. Wow, can I have it at least appear in scientific notation? Maybe, maybe not. I don't know. Oh, there it is. There's the scientific notation number. So this actually makes it a little bit easier because in the scientific notation, I can see that the number is 2.08. And then here, E notation. So it's times 10 to the power of 25. And I see that in my question text here, I already have times 10 to the power of 25. So really the only thing I need to put in here is the leading part, 2.08. So 2.08. That should be the correct answer. Let me put it in. And what I want to show you is a second way to put the numbers into a calculator in case you are using one of the calculators where you can't use the E notation. So let me start from the beginning. I have 100 and then 1,000, so 3 more zeros. 1, 2, 3. 100,000 Pascal times 0.8 cubic meter divided by, and my calculator lets me do the parenthesis. So this is what I'm going to do. Start up parenthesis and then type in 1.381. 1.381. So far I haven't really changed it. But now what I'm going to do for a calculator where I can't put it on, use the E notation, I still have the option to use a general purpose exponential notation. So what I'm going to do is times 10, that's what I'm putting in for X, and then I put in this. So you see that I have 10 raised to power of 23 or minus 23. And since I'm still within the parentheses, here I can do times the temperature, 278. And when I put in equals, I get the answer, and you can see that it's the same answer I got before. So this is how you calculate this question. Let me keep going. Question, let's see, question 6. Oh yeah, here you have to look up some numbers, I think. It says the same heat transfer into identical masses of different substances. Okay, that's the background. Okay, how much does the temperature rise when 8,000 joule of heat transfers to 1 kilogram of each of the material below? So I have water, concrete, and steel. All right. So you know, when you're not sure what to do, hint is what I would recommend. I am trying to be helpful. It says review something. All right. Heat capacity, look up specific heat of each of the substances. Okay, so I'm gonna need to look that up. Oh, and it's giving me an example that I should follow. Calculating the temperature increase. Okay, so I'm gonna look for that example. All right. So that's the textbook section, which, hopefully you read it, but sometimes, it's a long chapter, and I can understand if you have skipped it. When the hint links you, that's where you go. And this is the basic expression that we are using actually. It relates the heat transfer to the temperature change through the amount of the material in mass and what's called the specific heat. So this gives you the necessary information, but since I also gave you the specific example to look at, let me go to the example. I think it's tied to this one, yeah. Calculating the temperature increase from the work done on a substance. All right, so you should read this in detail. For right now, I'm just going to look at, here it is. So it took that equation from above and solved it for the change of temperature. So let me just copy this so that I can just use it. The derivation for this is similar to that other derivation that I did. So I don't think there's much value in me repeating that. So let me just write this down. The change in temperature is equal to the amount of heat transferred divided by mass of the substance times the specific heat. Oh, I need to look up specific heat of the three substances I remember saying. Let me just copy that here so that I have it to refer to. I believe the substances were water for 186, and let me go back up so that I can see what it was. The unit, okay. And unit is good to keep track of to make sure that you did everything right. So joule per kilogram times degrees C. All right. Concrete was, I think, one of the other substances. So that's 840. So specific heat of concrete is equal to 840, same units, joule per kilogram degrees C. I don't know if I remember the last one. Was it steel or aluminum? Steel, okay. So, here it is, iron, steel, 452. So specific heat of steel is equal to 452 joule per kilogram degrees C. All right, so all I need to do is plug in the numbers. So I'm given the amount of heat there. So let me just remind myself that this is the Q in units of joule. So you can see that, and the amount of mass is 1 kilogram in unit of kilogram. And you can see kind of staring at this expression here. If you are putting in the units of joule for heat, divide by the kilogram for mass, and you use the unit given here for the specific heat capacity, joule per kilogram times the degrees C. Then you see joule cancels joule, kilogram cancels kilogram, and I have 1 over degrees C, and this is equal to degrees C. And that's the unit that I'm answering in. So everything checks out. All I now have to do is just to plug in the numbers into the calculator. So let's see, clear everything. Yeah, let me just plug in the numbers. So the heat is 8,000 divided by, mass is just gonna be 1, so I'm not gonna plug in anything for that. So for water, it'll be 4186 for specific heat capacity. So that's 1.91 degrees C of change, 1.91. All right. Okay, let's keep going. For concrete, it's 8,000 joules, same amount of heat, divided by 840 joule per kilogram per degree C, and 1 kilogram too. Okay, so I get 9.52 degrees C as the temperature change. Finally, the amount of the temperature change in steel is given by 8,000 divided by the specific heat capacity of the 1 kilogram of steel, 452. So 17.7 degrees C, 17.7 degrees C. Now, so it's a calculation question, but I had a kind of a higher purpose in that I want you to see this vastly different amount of change of temperature for the same amount of material and the same amount of heat. In fact, one of the kind of special thing about water is that this amount of specific heat capacity is it's unusually large. And what that means is that for the same amount of heat absorbed, the amount of change of the water temperature will be smaller compared to almost any other substance. And this is, by the way, something that drives a lot of microclimate, especially in places like the Bay Area, where you have a clear boundary between the water and the land mass, and depending on the daytime and nighttime, the temperature of the land mass changes more quickly, and that drives a lot of the microclimate that you see in the Bay Area. So, all right, let me keep going. All right, suppose you're mixing some amount of hot water at the temperature of 76 degrees C with the cold water at temperature 1 degree C. Calculate the temperature of the mixture in each of the scenarios below. All right, let's see what the hint says. If you, yeah. So you are welcome to take a look at this example. I believe it's the example that, did I get to it yet? Here it is. That's the example. So you can follow the algebra here and go through that. You're welcome to do that. Let me give you a little bit of a shortcut. This question in particular, I gave you the two objects as hot water and cold water, because that'll make the situation particularly simple. And you can, in fact, even use some amount of intuition for this. So imagine, so let me kind of walk you through that intuitive calculation that you can do. So you have hot water at this temperature, and you have cold water at this temperature. And when you look at part A, I hope you see that you are mixing equal part of hot water with an equal part of cold water. So if you simply had to guess, what would you guess? How would you guess the temperature of the mixture should depend on the temperature of the starting ingredients that you are mixing? Now, if you somehow said it should be the average, then yeah, you're right. That seems sensible. And if you actually go through that example and do all the fancy algebra, you'll get the same answer. I mean, all the fancy algebra, it's useful to figuring out the answer when the answer isn't obvious. But when the answer is obvious, we can use the fact that so to take the average here, you add these two numbers. So it's a 76 plus 1. Okay, and then you divide it by 2. So I get 38.5. Let me put that in, 38.5. And yeah, that's the correct answer. Now, it gets a little bit more complicated with this and this. And oh, I don't think in this class I shared what's called the weighted average yet. Well, let me quickly do that. So I guess, how do I put this? So when you took the average for part A, this is basically what I did here. So, so to calculate the average temperature, what I did was, all right, I have the hot water temperature plus the cold water temperature and divided by 2. To do something called weighted average, I can modify this expression here. So this kind of regular average, I can just do it fine this way. Now, weighted average is a kind of a more generalized idea of average. So here, in the first part A example, I just simply added the hot and cold water temperature because I had the equal amount of them. They had the equal weight. One wasn't more important than the other. So, you know, I could be explicit about that by saying, all right, 1 times the temperature of the hot water plus 1 times temperature of the cold water. And in the denominator, instead of 2, I could say, oh, that's the sum of these weights. So 1 plus 1. So this is the regular average that you already know. that's expressed in the language of the weighted average. These things that I wrote here, these are what we call weights. And I'm calling this more generalized idea of average because this allows you to handle more general cases like this one, dealing with an unequal amount of water. So here, cold water, I have 4 times as much cold water as I do the hot water. So the temperature of the cold water is going to matter by 4 times as much. So in the case of part B, this is what I should be putting the numbers into. So my average temperature should be, all right, the hot water, it has a weight of 1 times the hot water plus the cold water, now it has a weight of 4. I have 4 parts cold water for every 1 part hot water. Divided by, now what I'm gonna divide by here is gonna be the sum of these two weights, 1 plus 4. You can almost look at it this way. You are taking an average of 100 milliliters of hot water with 1 unit of 100 milliliter of cold water plus another unit of 100 milliliter and 2 more units of 100 milliliter of cold water. So this 4 times it kind of just it's making this calculation a little bit simpler. So let me plug in the numbers here. So it's gonna be, oh wow, that's busy. Okay, it's gonna be, let me have a, do I need a parenthesis? I don't think I need a parenthesis, okay. So it's gonna be the temperature of the hot water, 76, and then have 1, I'm not gonna multiply that, plus, and my calculator actually does the order of operation for me. So if I put in 4 times the temperature of the cold water, 1, it'll kind of work everything out. So that gives me the numerator, and I divide by, I can do 1 plus 4 in my head, that's 5. So I get 16. So 16 degrees C should be the temperature for part B. So part C, it's the same idea. Let me just replace some numbers here. So I see that 450 is 9 times 50. So for every 1 part hot water, now we have 9 part cold water. So let me modify the denominator here because the weights are now 1 and 9. So I should be adding 1 and 9 for the thing I'm going to be dividing by. So, all right, same numbers to plug in. So it's going to be the temperature of the hot water, 76, and times 1, plus this time 9 times temperature of cold water, 1, equals, I get that, divide by 1 plus 9 is 10, so 10. So 8.5. And hopefully this all agrees with your intuition. If you are mixing small amount of hot water with a lot of cold water, then you wouldn't expect the resulting water to be very hot or even barely warm. So, all right, let's keep going. So question, oh, all right, I think that's enough. All right, so the answer is in terms of in the order of the amount of heat energy that it takes, is that the vaporization of water takes the most heat energy, and then it's gonna be the heating the water up. Wait, heating the water up? I actually need to draw. It's a kind of close. It's not very different. It's okay. Heat energy, it goes from here to about here. So it's a heat energy of about 100 calories or whatever. All right, that's how calorie was defined actually. And for water, it looks like it's slightly less. So I'm going to say heating the water up takes the second most, and then melting the ice takes the third most,
and heating up the ice takes the least. And the answer, yeah, it's right. And this is actually how you would kind of figure this out. You can do this visually. The kind of the intervals here are what shows you how much heat energy takes to go through this much transition here. So you see that to heat up the ice, it takes about this much, and I can kind of look at it here. So this looks like about maybe 40 calories. And then going from here to here, that's probably about 80 calories. From here to there, it's 100. And then it takes way more energy. It takes almost more than 500 calories to evaporate all that water. And more than 500? Yeah, more than 500. So, so the thing that I think it's useful to have good intuition for is just how much energy it takes to vaporize or boil water into steam. That's kind of the thing to know about. That's why actually if a hot steam has more danger to scald you than just the hot water does. Because as the steam condenses onto your hand, it's releasing a lot of heat. So yeah. So anyways, yeah, so this is a more of a conceptual question, but I felt like I had to cover it now. So let me keep going. Let's see. Okay, so here's follow this tutorial to figure out. Should I have you just to do the tutorial? Yeah, let me do it. I think I have time. Yeah, and I said I will do all the calculation questions. So I mean, let me have the hint open, because my recommendation is that you do try to follow the hint. As I keep saying, I'm trying to be helpful. So in particular, it says, look carefully at units of specific heat of water. That actually gives a fair amount of information here, because when you look at the specific heat of water, this is what it is, and this is joule per kilogram per degrees C. It kind of tells you how you should be combining numbers. So you have this as the specific heat, 4186 joules per kilogram times degrees C. So we are looking for, so we are trying to change the temperature from 25 degrees C to 0 degrees C. And we are looking for an answer for heat energy in the unit of joule. And this is where I want you to kind of take a hint from the units here. I have joule on the numerator, so that's the unit I want to end up with. So really all I have to do is get rid of these units, kilogram and degrees C. So the way I can get rid of them is I can multiply by these numbers. So if I multiply by 20, the change of temperature from 25 to 0, so that'll be, the change is just 25 degrees C, And okay, so that's gonna get rid of degrees C here. Now I still need to get rid of the kilogram, and here it is. I have the mass of the water. So times 0.25 kilogram. So the kilograms will cancel out, and we should be left with the joule when all this calculation is done. So that's kind of the hint. Without knowing, I mean, you can also refer to the section that I was referring to earlier, but you can be guided, hinted by the units to put together this expression. So let me just plug everything into calculator. So I have 4186 times 25 times 0.25 is equal to, wow, that's a big number. And I think it's actually supposed to be that big. All right, I need to remove 26,163. 26,163. joule of heat energy to cool this water to 0 degrees C. All right. Okay, and then it says, given that the latent heat of fusion of water is that, how much ice needs to melt in order to cool down the water to 0 degrees C? Oh, I see. It's something about mixing stuff. So once again, I follow the hint. It says you have the amount of heat energy needed. Right, I calculate this. So I guess that's the heat amount of energy that I need to absorb by the ice melting. And when I look at this here, I have joules. Okay, so that can be matched up to that joule of heat energy. And here the denominator for the unit to look different. It's not kilogram degrees C, it's just a kilogram. And if you think through what latent heat means, this should make sense, because what latent heat describes is the heat transfer that takes place with the change of phase, change of solid to liquid or liquid to gas. So while you have the change of phase happening, the temperature actually doesn't change. That's why you are not dividing by any temperature. So, so this is what I have. Let me just kind of write it down so that I can start manipulating it. So latent heat of fusion is 334,000 joule per kilogram. And I'm looking for kilogram of ice. Oh, so my kilogram is on the wrong side. I want that on the numerator, not the denominator. So what I can do is I can kind of imagine taking the reciprocal of this, 1 divided by this whole thing. When you do that, what you will have is something that looks like this. 1 over 334,000, whatever that number is. And the reciprocal of the unit is kilogram per joule. All right, so to get the quantity that's in kilograms, all I have to do is get rid of joule. Oh, and I have that joule number from before. That's, you know, the energy that I need to transfer. So let me do it here. Times, so 26163 joule. And let's see what we get. So, oh, I already have that. So let me actually take the number and divide it by the number there. 334,000. Okay, let me type in equals. So I get the answer of 0.0783 kilogram. Oh, it's kind of small, all right? 0.0783. Kilogram of ice is needed to produce a mixture. So when this much ice has melted, it has absorbed this much heat energy, cooling down water at 25 degrees C down to 0. So yeah, good. And then there's a kind of follow-up remark that you can read, and hopefully that makes sense. So the point of the calculation in this question especially is to kind of give you intuitive feel for the kind of size of the heat transfer that takes place with these processes.